Hi, everybody, and welcome. In this session, we're going to be talking about some of the use cases of sound namespaces. In particular, we're going to cover some of the new features that are cut into the NVMe standard for in-place updates and transfer high queue depths. So Kansan and myself will be running the session. Kansan, do you want to introduce yourself?
Hi everyone, my name is Kanchan and I will try to cover the Linux IO stack part of the ZNS feature. How do we go about plumbing them into the stack? Back to you, Javier. Thank you.
So I'm Javier, I'm also a software engineer, and I'm going to be covering the introduction to sound namespaces and then take a little bit on the user space stack. So if we get started motivating, why do we need a new interface? So SSDs are already mainstream. They offer great performance. They're easy to deploy in plug and play replacement for hard drives. And they're getting to an acceptable price in terms of $2 per gigabyte, right? However, there are three main problems that have not yet been solved in current solid state drives. The first one is the problem of the log-on-log. So this basically means we have a lot of work in software stacks that do a big effort in trying to do append-only workloads. You can see this at application level, like log structure merge trees. You can see this at a file system level with file systems like F2FS or ButterFS that try to be log structure and more flash friendly. But at the end of the day, the abstractions that we have in place for block devices make that whatever tries to be serialized in the host is being moved around by the different layers. So being able to have a direct data placement policy that allows us to leverage those data structures directly through the device would allow us to get better write amplification, better over provisioning or less over provisioning, and remove the device data placement. And this effectively has an impact on the total cost of ownership of solid state drives. The second part is about multi-tenancy. So we're still yet to solve the noisy neighbor problem. There are solutions out there, but most of them are still following an implicit model. Having an explicit policy where host software is able to place data on different LDA ranges and have control about the QoS is still something that we need to solve, and we believe that ZNS, as we're going to present it today, can help in that path. The third part is cost. As I mentioned before, putting those two things together, we make it easier to adopt technologies like QLC or later down the road higher bit counts. By removing the 1 gigabyte per terabyte mapping table for the 4K mapping, we can reduce the DRAM on the device. And reducing these log-on structures for data placement, we can also reduce the OP and write amplification. So moving quickly through use cases that are targeted for sound namespaces. I believe one of the first ones that we're hearing about, many people talk about it, is archival. This has a very specific need for adoption of QLC. And coming back to the TCO, reduce write amplification, over provisioning, and DRAM. This is great for cold storage, trying to introduce solid state drives into the cold storage tiering. We see this use case where we have very large zones that are able to be mapped to very large objects that are already immutable. This means that the host side can do all the work that it needs to do for updates using other technologies, either another layer of SSDs or some persistent memory, NVDIMMs, whatever. And once those large objects are immutable, then they are directly persisted into the ZNS SSD. Another use case that we're starting to see, which is very interesting, is that we are calling log IO. And it has a lot of similarities with the archival use case. It is also about facilitating QLC adoption with probably TLC coexistence. It also tries to leverage these existing flash-friendly data structures, log structure, still reducing the TCO. But one of the main differences with the archival use case is that we're not necessarily targeting very large objects. Instead, we are targeting a normal storage stack that is able to use ZNS, but not necessarily be at an archival cold storage level. And for this use case, we see the need for smaller zones. This is essentially because on workloads that are not targeted for archival, the objects are being mapped are not that big. So if you look, for example, at log structure merge trees, we have different levels. The first levels are not in the orders of gigabytes, like that would be a large zone on a QLC device. We see some megabytes, hundreds of megabytes, maybe, depending on the use case. So having the possibility to map those to smaller zones and then have the ability to put these zones together to be able to map to larger objects is of importance for this use case. Gathering the small objects on a single large zone would incur more garbage collection. The third use case, which is a little, it is different than the two previous, is about IO predictability. And in this case, we do not care much about the type of NAND that we're using. What we do care is that the data placement within the zones is offering a level of QoS across different zones, meaning that we can put different tenants on different places of the SSD and different zones, and we will have some guarantees in terms of isolation across these zones. In this example, you could see that if application 1 is write heavy and application 2 is read heavy, we would not see the outliers in the read heavy workload when both applications are running at the same time in this particular multi-tenant environment. So now, running quickly through the main features of ZNS, we have different talks in this conference presented ZNS, so we're not going to spend much time. I believe there are two things that we need to cover to understand the basics. First one is ZNS allows data placement at a different LBA ranges. How these zones are configured depends from vendor, depends from product. We have different configurations here, and I'm sure there are many others. The second important part is about the state machine. It is important to understand that this state machine is being managed by the host. So whenever we want to write to zone, we need to open that zone. We have different ways of doing that. And whenever we want to reuse the zone, we need to reset the zone. And this is an important concept because it's what allows host garbage collection to take place. So the host is in charge of moving valid data from a zone that it needs to reuse by resetting. This essentially breaks all data movement within the controller. The third part, which is write operation, I'm gonna delay it to a slide in the future because we're gonna talk about different write models used in ZNS. The specs are public, so you can go to that link and get the different TPs that are affecting ZNS. So 56 for namespace types, 53 for the ZNS spec, and then right now we have 61 for single copy. So the write model, once you have this ZNS model, we again see three different ways of writing to a ZNS device, right? First one, most simple, obvious, is writing at Q.1. Why is this necessary? So this is because on a zone device, we have the concept of the write pointer. So the write pointer sits at a specific LBA. And when we send IOs, write IOs to that particular zone, we need to guarantee that IOs are completed before we send a new IO to the zone. This is because of the non-ordering guarantee in NVMe. This is a limiting factor because on large zones, this essentially means that we are not able to saturate the NAND array underneath. So some use cases are okay, but this is a limiting factor. In order to overcome this, we have two ways of writing. One is the what we're calling the zone append command that has been standardized as part of the ZNS spec. And it essentially means that we can send a nameless write to a particular zone without necessarily pointing to the LDA where the write pointer is pointed at. So we can send several IOs of different sizes to a zone, and then the controller will take those IOs, will place them in the right order, and return the LDA value to the host. Then the host is responsible for remapping in the completion path. This has some implications on how the host stack needs to deal with it, but it is a good way to deal with larger zones where we want to increase the queue depth. The second way of writing when we don't want to do queue depth 1 is about zone striping. And this essentially means we do queue depth 1, but across smaller zones. So essentially, the host software is responsible of deciding to which zone is being written in parallel. This striping gives the flexibility to the host to choose where it wants to write and how it manages the latency versus the bandwidth parameters when it is designing how storage is being used. It also has the advantage that it is using traditional write operations. So changes to the host stack are really minimal. And now, that is what is the basic concept of ZNS as we have it today. What is coming new is what we're calling the zone random write area. So this is still a new TP. It is under development on the NVMe task force. So we are going to talk about the main concept, but we are not going to talk about the specifics about the TP because it is being yet finalized. The main motivation for this zone random write area is, well, what if we have a workload where we want to eliminate this constraint about the write pointer? So there are cases where you want to be able to go a little bit back in time because your data is not, your workload is not fully sequential. There are small in-place updates primarily targeted at a metadata. And instead of having to serialize them and then do extra garbage collection, which means more write amplification, and it's kind of counterintuitive for ZNS, we essentially have a mechanism that places a window in front of the write pointer. And within that window, we can do any in-place updates we want to until the data is immutable. And once the data is immutable, we essentially flash that window to the media and advance the write pointer where a new window begins. So this has two interesting properties. Obviously, the first one is that you can do updates on a zone namespace. The second one is for the size of the window, you essentially don't need to respect the strict in-order policy, meaning that you can increase the queue depth. IOs will arrive at any order, and within that window, that will be okay. There will be no problems and write errors due to the write pointer. And we see this beneficial for people that are having issues adopting the append philosophy. And we also see this useful for people that have this inbuilt metadata into their IO path, and then they need to do these updates, some file system checkpoints, some applications that are putting metadata either intermediate within the object or at the end of the object, things like that. Those are the main use cases. How we plan this, Kanchan will tell you in a little bit. The second new feature that is actually already ratified and published is simple copy. This is interesting for some namespaces because once you have to do host garbage collection, we have the problem that if you imagine a modern disaggregated storage, your storage might sit on the other side of some sort of fabric. When you need to do host garbage collection, you basically need to move the data from your storage node all the way to your compute node through whatever fabrics you have in the middle, go through your CPU root complex, and then come back. This consumes PCI bandwidth, any other fabric, RDMA, TCP/IP bandwidth you have in the middle, and is consuming your CPU cycles. Simple copy is essentially a new command that allows us to choose a number of LBA ranges that can be on several zones. That is a scatter gather list. You can choose a large number of them, and then you select a single LBA range on a zone, and by sending that command, data within the controller will be moved. So you are sparing all the data movement and CPU utilization. This can actually be used for other things that are of ZNS, but it is primarily targeted for this. It is great when you combine them with things like some random write area, because then you can have different different objects for your incoming user data and your garbage collected data, and at the same time put the metadata how it fits. We see different customers using this as a way to better adopt ZNS on an existing and mature software stack. And right now, Kanchan, you can take over and guide us how we do this on Linux.
Thank you, Javier. So the picture here is the bird's eye view of the Linux ecosystem for GNS. At the bottom, we have the ZNS SSD, which implements device side of the GNS TP. Parallel to that, we have QEMU, which implements the same TP and presents emulated GNS device. And that helps in the faster development and testing of the software stack. Moving upwards to the kernel, from 5.9 onwards, GNS support is present in NVMe driver. Coming to the block layer, a lot is inherited from the infra that was added for SMR device. And GNS specific new things like Zone Append Command is also present. On the FS side, F2FS and Zone FS, they can support the Zone devices already, while work is in progress for ButterFS and GFS. Now, if we talk about taking some of this goodness to the user space application, syscall interfaces need to be built. And a good amount of work is in progress towards enabling sync and async interfaces for new features via IOUring, libIO, and sync-ones. Coming to the user space, there's an array of softwares getting GNS updates. There are management tools like BLK Zone, NVMe CLI, performance and test tools such as FIO and block test. A couple of zone-aware file systems and DBs, and there are libraries such as XMBPME, which is going to help application development by providing a single unified API for multiple backends.
So I will talk on how we can go about plumbing some of the features that Javier mentioned earlier in Linux IO stack. While kernel mode obviously get to use the new features first, one of the important goals that we are after is making these features reach to the user space applications directly. With this application, which like to do things by themselves, such as user space file systems and DB, they get more control, flexibility, and hopefully better efficiency. And towards that goal, we believe that the block device interface coupled with async transport, such as URing and AIO, can be handy. Starting with the zone append. So as I mentioned earlier in the previous slide, that zone append command is already present in the kernel, and in-kernel users are able to make use of it. But when it's about exposing it to user space, there are a couple of challenges. The first one is how best to return where append landed, because existing system calls don't really have a very clear way to return the offset. And another issue is how to ask for zone append and not for regular write. Essentially, append is a variant of write. So application needs a way to tell when it wants append and not a regular write. So the way to solve these problems in AIO, first I would talk about AIO because it is much more straightforward compared to URing. So in case of AIO, we could use an unused field result2 to return the offset to the user space. And append is triggered by combining two flags, existing RW_append flag, and a new one which tells the kernel to report the offset directly. This will make more sense when we see the URing scheme. So we'll get there, yes. In case of IO URing, we didn't really have any unused field like AIO, but it was possible that application can pass a pointer along with the SQE. So so when application passes a pointer to the URing can update it when it receives the completion from the lower layer. And as far as trigger for the append is concerned, it is same as AIO, except that here the flag tells the kernel to report the offset indirectly because it is expecting a pointer. So the flag should convey the same. The last point about this whole interface is that it is not yet frozen, but a lot of debate has happened in the Linux kernel mailing list to arrive at this. So I believe the final interface wouldn't differ much from what I described here. And before I move to GRWA, bit of touch base on zone write lock. So when multiple writes are issued simultaneously on a zone, either by multiple applications operating on the single zone, or one application sending writes at higher QD to the single zone, in both the cases, it may lead to error because of the violation of sequential writing within a zone rule. So MQ deadline implements a per zone write lock. So many writes can arrive to the MQ deadline, but it makes sure that at max one write is dispatched to the driver on a zone, and that eventually leads to QD1 per zone result. In case of zone append, it is avoided. The zone write lock is avoided, and the reason is that the caller is fine with out of order placement as long as it happens within a zone. So multiple appends can be outstanding on a zone, and they would get completed within the zone at some point of time, and caller will get the location when it receives the completion for those append commands. So that's how the multi-QD is achieved in case of append. Now coming to GRWA, it is pluggable to a zone. So GRWA buffer is attached or removed from a zone via ioctl. That's the setup part of it. The nifty thing is that during write, nothing spatial is done in the sense that no opcode, new opcode is not required. It travels like a regular write. And the GRWA backed region of a zone can be treated like a conventional zone conceptually, as it can be randomly written. So higher QD is possible. and in-place update is allowed. So MQ deadlines write lock is skipped for GRW enabled June. Coming to simple copy. So because simple copy is a new operation, we had to add a new opcode in the kernel, which is called request op_copy. With that, one can prepare a bio, package a list of source LPA in the payload, and send it down to the NVMe for processing. And this whole thing is presented to the application via ioctl for synchronous processing, and to uring or AIO for asynchronous processing.
This is how we can go about leveraging GRWA and simple copy in the F2FS. F2FS is used as a reference here. It is possible to apply the same underlying idea to the other log structure software as well. A couple of things are required to set up F2FS on zone devices. So it has maximum 6 open zones, hot, warm, and cold, and 2 sets of each, one for data, other for node. The allocation and garbage collection unit is section, which is collection of 2 MB segments. For zone devices, this section is mapped to the device zone size, and it is made sure that F2FS disables the adaptive logging and remains in strict LFS mode, so that writing to the holes is skipped. Now, there are a couple of new problems with respect to GNS. Because F2FS metadata requires in-place update, and GNS does not really have any conventional zones. So a multi-device setup is required. And given the large zone size, it is possible that garbage collection takes more time, which can affect the user applications during foreground GC. And obviously QD1 writes are speed dampeners, be it during the regular writes or be during GC. So how we can go about solving some of the problems? So some of the metadata which gets updated frequently can be created out of the GNS itself, such as checkpoint, given that GRWA allows in-place update. The higher QD can be obtained by using append or GRWA. And simple copy is going to help in offloading the data movement, the GC data movement to the device. And by using the GRWA in-place update, some of the writes on the flash media can be avoided. So there's an example here which shows the recurring updates happening on a file. Few blocks are getting updated more frequently than others. In this case, the blocks 0 and 1 are getting updated twice, while the block number 2 and 3 are getting updated only once. When we run this update sequence on GRWA disabled zone, which is shown in the left-hand side, it produces 2 invalid blocks. Reason being, block 0 and 1 are getting updated twice. And but the same sequence, when it is run on a GRWA enabled zone, which is shown in the right-hand side here, it doesn't produce any invalid block because in-place update happens in the GRWA buffer, and it doesn't really reach to the underlying flash.
So here are some early performance numbers with GRWA and simple copy. The right-hand side plot here shows the trend we see with 4 KB writes pumped at QD16, and the engine used here is uring. The blue line shows the bandwidth, which scales as we increase the number of zones. We are writing these zones in stripe fashion. And the reason of this hike is that as we increase the number of zones being written concurrently, the workload gets more parallel. The orange line shows the bandwidth with the same setup. The only difference is that the GRWA has been enabled on these zones, which gives about 20 to 25% of increase in the bandwidth. The bottommost 2 plots are for simple copy. In this experiment, 64 zones are being copied, either via read and write, combination of read and write, or via simple copy command. So simple copy takes about compared to read and write, it saves about 30% of the time. And the host CPU consumption also goes down by about 500%. And one last note about all this data is that it's obtained from FIO. FIO already has the ability to run zone compliant workload. And we have added a bunch of new features: simple copy, GRWA, and striped writing among zones, to name a few. Zone append is not shown in the slide, but FIO patches are already out, implementing the user interface, which I talked about in the previous slides. And at this point, I will give the control back to Javier for the rest of the session.
Thanks, Kanchan. So now that we've covered the kernel, let's talk a little bit about a library that we're calling XMBPME, and I'm super excited about it. I'm just going to talk quickly through it because we do have a presentation by Simon, who is going to get into the details of how XMBPME works, where are the performance numbers for conventional namespaces, and what you can expect from it. But in essence, XMBPME is a library that sits right underneath an application, and it provides a single API for applications to be able to use any NVMe namespace types and be able to run through a number of different IO backends. So if we choose Linux, we have different possibilities when it comes to submitting IO. If you go through in-kernel, we have a traditional libIO, normal peer-read, synchronous. In the last year, we've got an IO uring, and we also have possibility to run SPDK. All these are great. The problem is that you need to become an expert on each backend to be able to really take the most out of it. And we have experienced that people that are an expert in one backend, they tend not to be data experts in different backends. So you can get 100% out of one thing, but you end up losing a lot of the performance on or the features in another backend. And that's where XMBPME can help. Because through a single API, we start really thinking about how the backend is doing things, and you can submit a IO and change the backend at runtime, and do not necessarily need to make changes to the application. There are several things that we do in terms of abstracting the backend. We also try to abstract things that are as different as the threading model if you compare SPDK to IO uring. And we even target changes of operating systems. So right now, as an application that is running on XMBPME can run on any of the Linux backends there, but it can also run on FreeBSD through SPDK. And we're at the moment implementing support for the normal IO path in FreeBSD and through Windows if you want to do that too. But again, Simon will talk you through that, so I really encourage you to go see his session. And the second part that I want to talk about is, well, what happens when you want to implement ZNS on your software stack, but you either do not have the hardware yet, or you have new features that you want to get that are not in the samples that you have at the moment. Well, we've done a lot of work in QEMU to be able to support all new namespace types. So again, Klaus will have a dedicated talk at the SDC where he's going to talk about the rewrite he's done of the QEMU NVMe device and about the features that he has implemented on ZNS. But a little bit of a spoiler, we have support for all the ZNS, we have support for a simple copy, all the patches are posted, and now we are working on how we put all the work that is being done from different sources together. And as soon as TPs like the some random write area are ratified, we will submit the patches for those two. One small comment that I think is also interesting A QEMU is mainly an emulated device, so you cannot really run performance number through it. But we're doing some work in what we're calling NVMe low latency mode, which we expect would allow us to use QEMU sort of like a no block device in the kernel, but not stopping at the block layer, but stopping on the other side of the NVMe driver, so that we can really test what is the performance and the latency that we should expect when using different paths and different IO paths, but also different parts of the NVMe driver, or even different NVMe drivers for that sake. So I believe this is the last part of the content. And this is about, well, when you put this all together on an application, what happens? We chose Roxby. And this particular implementation of Roxby is through a library that we call XCTL, which is also available on the OpenMPDK website. XCTL basically allows us to abstract the logic for LSM3. There are many databases like Roxby. You can choose examples like Sandra, some other more proprietary LSM3s that use the same logic. And we wanted to abstract that away so that the actual backend that makes it to the application is very, very thin and easy to maintain. If you think of Roxby, you can think of the HDFS backend, for example. And basically, the approach we've followed is that Roxby through XCTL and then through XMBPME chooses a pool of zones, and it is choosing a striping approach with a smaller zone so that we can really leverage the small objects on the first levels of the tree and then grow the size as we go to the deeper levels. And while we strive, we use the sum random write area as a way to update the metadata at the end of the SS table. You can run Roxby with a fully serialized SS table, but you will incur a little bit more of write amplification. Using the sum random write area, you can allow these small updates that happen at the end of the SS table metadata and reduce the garbage collection that is needed afterwards. We also implement the simple copy to do the garbage collection. This is same logic as Kansan has mentioned before, but on the application level. And it's fairly easy to plug the existing garbage collection in Roxby to leverage simple copy. And at the moment, obviously, we're using XMBPME. When we go through the kernel, we use the path that Kansan has described. When we go through SPDK, we use directly the logic on XMBPME through the pass-through BDEV. Some early numbers that we want to share. So in the slides, you have a screenshot of a Grafana interface, but I think that we can go through a live demo, or as live as it gets in this situation. So here you see Roxby workload. On the left-hand side, you have the terminal. In this particular example, we're running an override workload, but the device has been preconditioned with a full write workload. And what you see here is basically three numbers that I believe are of interest. So the first one is in red, the write amplification that this workload is generating on an X4 file system without any form for sound support. So the way we're measuring this is number of bytes that come from user space and number of bytes that are leaving the file system only for the data part. This is an important differentiation because we're not interested in measuring metadata at this moment. We just want to see how the way we're organizing data and we're mapping it to different, in this particular segments and their blocks, has an impact when compared to how we map data to zones on a zone-aware application or file system. The next step is what you see in yellow. That is F2FS with zone support. in this case, we have two different block devices, one conventional for the metadata, one zone for the data, and we do the exact same thing. We run the same workload with the same preconditioning, and what you see is that there is a big improvement just by the way we're mapping the data in terms, again, of number of bytes that enter F2FS and number of bytes that are leaving F2FS on the data zone namespace. And then in green, you can see the same workload, but running on our RoxDB backend on XCTL, XMBPME, in this particular case, running also through the kernel, so that this shouldn't have any impact, but just to be complete apples to apples. What is important to mention here is that the difference that we see over time, just on the software level, is very relevant, because this number, at the end of the day, you need to multiply it by the run amplification that is being generated by your device. So we can obviously not speak about the run amplification generated on the SSD. This is vendor dependent. It depends on the workload. It depends on many other things. But if you do know something about the run amplification on your device, you can use these numbers as a way to factor the real run amplification that you are generating, besides the real run amplification that RoxDB is in itself laid on top. In this case, that's what you see around 2x on the bottom. So, real life examples, this tells us that a very flash-friendly workload can gain us, in the realm of 3 to 5x. Workloads that are actually not that good with the ROM preconditioning, we're talking between 15 and 20x. So, I don't like putting specific numbers because it really depends, but I hope this gives you an idea of the benefit that we are getting from a software perspective when you are running an application that already understands log structured objects that can easily be laid on top of zones. We also have some early numbers on the some random red area, which not only shows you that we can get the advantage of the implex update, but as we do striping, if we choose to use larger zones that span across several NAND blocks, then we also get the advantage of the better bandwidth. So I think that's all. We've gone through what are the basic concepts of ZNS. I'm sure after this conference you got that covered. What are the use cases that we're targeting? That's important to understand, because when you're moving from an archival only use case to a more log IO determinism, new features, the new features that we're bringing to NVMe are becoming more and more relevant, especially if you're thinking of adopting Open-Channel SSD use cases through ZNS. Kanchan has gone in detail through the ecosystem in Linux. And then we've covered, other tools, XMBPME, the work that we've done in QEMU, and some of the Roxby part. So, I hope you enjoyed. And if you have any questions, you're very welcome to reach out to Kanchan and to me directly. And again, I encourage you to go and see Simon's talk, Klaus' talk, and the rest of the Zone Storage track, where we have folks from WD, SUSE, and Catalyst.io covering interesting topics from also QEMU, kernel, and different applications. So look forward to listening to your questions in the Slack, and thank you very much.